Okay, so today we're going to look at permutations. So our learning intention is to gain the knowledge, what we mean by permutation, and the skills in applying this to probability. So we'll be successful if we can define or describe what permutation is, and be able to use the permutation button on the calculator and solve probability problems using permutations. Okay. So if we have a question such as this, is how many ways can cards A, B, C, D, and E be arranged? Well, so we're going to have 1, 2, 3, 4, 5 possible options for the first card. Let's say we're not replacing the card, so once that card's down, we're not replacing it. So if I've got 5 for the first one, then I only have 4 for the second card, 3 for the third card, 2 for the second last card, and 1 card at the end. That is also 5 factorial. So we can type in 5 factorial. So there's 120 different possible arrangements for the 4 cards A, B, C, D, and E to be arranged. And some examples are we've got A, B, C, D, E. We got A, B, C, E, D. Got A, B, D, C, E. And so we've got 120 different possible outcomes for that. Yeah. What if I only wanted, how many ways can 2 out of the range? So I'm only having 2 of these. So we know that we have 120 examples of just that. But if I only want 2, then I've got to kind of think of I can have AB, I can have AC, I can have AD. Yeah. So when I'm not using all the cards, we call this a permutation. And so I want to figure out how many out of 5 cards, how many different permutations can I make with 2 cards? Yeah. So if I go 5 shift NPR, which is that X button, and select the 2 cards, I will have 20 possible situations. So there will be things such as AB, AC, AD, AE, BA, BC, BD, BE, CA, CB, CD, CE, DA, DB, DC, DE, and then EA, EB, EC, ED. So we have 4 by 5 options. So we have 20 possible solutions. Okay. So the rule is when we arrange only some of the objects without replacement, we call it a permutation. So according to the Nessa Extension 1 glossary, a permutation is arrangement of R distinct objects taken from N distinct objects, where order is important. So the number of such permutation is denoted by N permutated with R, and is equal to NPR equals N times N minus 1 all the way to N minus R plus 1, which is the same as N factorial over N minus R factorial. So the number of permutations of N objects is N factorial. Okay. So let's do some quick examples. So how many ways can first, second, or third prize be awarded to 15 competitors? So there are 15 people. So that is n. So n equals 15. And in this case, we want first, second, and third. So R is 3 positions. So we have n permutated with R. So we've got 15p permutated with 3. So 15, so shift times, so you see the NPR just above your times. There is 2,730 permutations. Okay. So, looking at the second example, so how many 4-digit PIN numbers can be formed greater than 6,000? Okay, so we have 4 numbers, yeah? The digits go from 0 all the way to 9, so 1, 0, 2, 3, 4, 5, 6, 7, 8, 9. So there are currently 10 different combinations. If we want the number greater than 6,000, it means that we have 4 possible situations for the first number. So we're going to either start with a 6, 7, 8, or 9. And then for the rest of them, we would have, once we've got the first position, there would be obviously 9 numbers left. Yeah, so if one of them was taken, there's still 9 others, and then that's 8 times 7. So we can calculate that individually. We can go 4 times 9 times 8 times 7. So that's 2016. Alternatively, using permutations, yeah, we start with that digit, but then we have, so there's 4 of those. Then we have, in here, we have 9 digits and 3 orders. So 9 permutated with 3. Gives us the same amount. Okay. And that's a permutation, where we have 9 numbers, but we're only choosing 3 of them. Yeah. So how many 4-digit PIN numbers can be formed if the last number must be a 5? So same thing. So we've got the 4 pins. If the last digit needs to be a 5, we'll only have 1 possible outcomes there. Removing that 5, I would have 9 here, 9 options here. I would have 8 options here, and I would have 7 options there. Yeah. So the same thing. So now I've got 9 times 8 times 7 times 1, so I've got 504. Well, as I said, alternatively, in this case, we've got the number of digits being 9. We only want to choose 3 of them, yeah, because one of them is set. So we've got 9 permutated with 3, or 3 permutations out of 9. So 9, it gives us 504. Okay. Cool. So next example, we've got, in how many ways can 5 thrillers, 4 horror, and 2 comedy DVDs be arranged on the shelf? Okay, so at the moment we've got 5 plus 4 plus 2, that's 11. So this would be 11 factorial. So the second part says, well, what if the DVDs have to stay together in categories? So we have to have the thrillers all together, then the horrors together, and then the comedies together. Well, let's just look at the thrillers first. There are 5 thrillers, so there must be 5 different ways to organize those. There's obviously 4 horrors, so there'll be 4 different ways to organize them, and then 2 comedies. Okay. But these are 3 kind of different units, yeah? Horrors, thrillers, horrors, and comedy. So technically, they're actually, if there's 3, there are actually 3 factorial different ways to do that, as if you consider that these are kind of individual units. Yeah. So this would be 5 factorial times 4 times 3 times 2, which is 34,560. Okay, let's look at some situations where there may be a restriction. Okay, so let's imagine the letters of the word mathematics are on a card. So how many different arrangements if the 4 vowels were together? Okay, currently in this situation there is 11 letters. There are 4 vowels. And there are 7 consonants. Alright. If we consider the vowels to be 1 unit, yeah, so A, E, A, and I were together, yeah, there's technically 4 factorial different ways for those to be arranged. Yeah, and each letter is different. Yeah, so the double A's, that's A1 and that's A2. Yeah, they're different. Okay, because they're on cards. Okay, so there's 4 different ways for the vowels to be arranged. But then there are so if that's 1 unit and there's 7 different consonants, then there are so 7 plus 1, there are 8 different units. Yeah, the 7 consonants as independent units and the vowel as 1 unit. So the different arrangements would be 4 factorial times 8 factorial. Okay, so there would be 967 possible ways, and 680 possible ways. Okay. Let's look at the first and last place being consonants. So as I said, there's 11 letters. Okay, if that was a consonant, and that was a consonant, so there's 7 to start with, and then there must be 6 to end with. There's obviously 11 letters, so we're taking 2 away, so there is 9 factorial possible ways for this to be arranged. Okay. So the solution to this will be 7 times 9 factorial times 6. So we get 15,240,960. Okay. What if the consonants T, T, and MM, and so the letters TT, AA, and MM were together. Okay, so what we want to do is we want to consider that this and this and this is 1 unit each. Yeah. Okay. So if I was taking that from, so there's 1, 2, 3, 4, 5, 6 letters taken away, so I should only have 5 other letters that can be arranged in different ways. Now, each of these units, remember that I said that each letter was different? Well, there's 2 ways for those to be arranged, and there's 3 lots of those. Yep, or 5 factorial times 3 lots of 2 factorial. If we plug that in the calculator, we get 720. So this should be 8, because yes, there are 5 letters left, but these are also a unit, so I've got to actually include that. So that should be 8 factorial times 2 times 2. So we get 241,920. Okay. All right. If there are no difference between repeated letters, how many different arrangements can be made? So if we have 11 letters, so that's 11 factorial, we want to divide the double by the double up. So we have 2 different ways the T's can be arranged, times 2 different ways the A's can be arranged, and 2 different ways the M's can be arranged. So 11 factorial over 2 factorial times 2 factorial times 2 factorial is 4,989,600 possible ways. Yep, so the number of different ways of arranging n objects in which R of the objects are of the one kind, such as the 2 T's, S objects are another kind, 2 A's, and T objects are another, such as 2 M's, is n factorial, so all of them divided by R factorial times S factorial times T factorial, where R plus S plus T has to be less than n. Okay. Another one we need to be careful about is arrangements around a circle. So we have Abby, Brian, Clarissa, and Dan. They sit at a round table. How many different possible seating arrangements? Well, if I put Abby here, then there are 3 factorials for the other positions. Yeah. But if we moved it around, so if Abby started here, then I could be Brian, Charles, Dan, or Clarissa, Dan, Brian, or Dan, Brian, Abby, Dan, Brian, Clarissa. Yeah. If we were to move them around, the position wouldn't change. Yeah. If it was A, B, C, D, and then I move them one spot, in that sense, the position hasn't changed. The arrangement has not changed. They're still in the same order. So when looking at circles, we're going to use, there's 4 possibilities. So in a circle, we actually have 3 factorial. So once we place someone in their position, there are 3 other options. So there are 6 possible seating arrangements when sitting around a circle. Okay. Let's look at the next example. So in how many ways can 6 people be arranged in a circle if 2 particular people are always together? Okay, here is my circle. I have 6 people. Okay. If they have 2 people have to be together, then I have 1, 2, 3, 4 factorial remaining. All right. But I'm not quite sure which way these people are sitting. So I actually have 2 factorial in the way the people are sitting. Yeah, so the final solution for this would be 48 possible scenarios. Okay. Looking at the second part, if I have if they have to be separated, okay. Okay, let's say I position someone there, so that's going to be 7 possible solutions. Oh, sorry, 6 possible solutions. Yep. Because one of them has to be separated, I only have, sorry, I don't want 6. Let's say I position somewhere. I've got 2 people. I want A and B to be separated. Let's say that's going to be A. Okay. I don't want B to sit B next to him. So then this would have to be C, D, E, or F. And this must be, let's say it was C. This must be D, E, and F. All right. So there are 4 possibles to sit there, and then 3 possible people to sit here. So there are 6 people, so I've cancelled those 2 out. Then I really only have 3 factorial remaining for the other seats. Yep. So in this situation, I've got 4 times 3 times 3 factorial. So I have 72 possible solutions. Okay. So the number of circular arrangements is the number of linear arrangements divided by the number of elements. So n minus 1 factorial is the same as n factorial over n. An example of that would be if you've got, let's say, n is going to be 7. So 6 factorial is the same, which is 720, is the same as 7 factorial over 7. Same number. Okay, and that's what we talk about permutations. So, to conclude, describe what permutation is. Well, permutation is the number of different ways of arranging n objects. Sorry. No. Okay. So, permutation is an arrangement of r distinct objects taken from n distinct objects where order is important. Okay. The permutation button on the calculator is the NPR, and on the Casio FX 82 plus, it's shift X. Yeah. So it's the shift X button. So we want the small n p r. Okay. And we can use this to solve probability problems using permutations. Okay, good luck.